Welcome to The Explainer. Today we're going to break down a concept that's, well, it's at the very heart of machine learning. It affects everything from medical diagnoses to whether or not you get a loan. We're talking about the bias-variance trade-off.
So let's start with a really great analogy. Think of an AI model like a pro athlete. You can train and train and train on the practice field on data you already know. But that's not the real test, is it? The true test is race day, when you're faced with new, totally unpredictable challenges you've never seen before.
And this whole idea of performing on race day brings us to this crucial concept called model fit. You can think of it as the ultimate report card for an AI. It's all about how well a model learns from its training, and then, more importantly, how well it applies that learning out in the real world.
So, in simple terms, model fit is just the measure of whether our AI can actually handle the wild, unpredictable conditions of race day. This is the true test of its performance, and honestly, it's where things get really interesting.
That's because every single model is stuck in this constant tug-of-war between two opposing forces. On one side, you've got bias. That's the error you get from a model that's just too simple. And pulling on the other side, you've got variance, which is the error from a model that's way too complex, way too sensitive. Okay, so let's dive into that first one. What actually happens when a model has too much bias? When it's just too simple for the job it's trying to do.
Okay, imagine you're looking at a graph with a whole bunch of dots scattered in a complex, curvy pattern. Now, here's the catch. The only tool you're allowed to use is a simple, straight ruler. No matter which way you turn it or angle it, you can just see right away. It's never going to capture that curve. It's just too rigid. And there's a name for this problem. It's called underfitting. The model is so painfully simple that it makes the same mistakes over and over again. It consistently misses the real story, the true pattern that's hidden in the data. Basically, it just hasn't learned enough.
So what does this actually look like in the real world, right? Where the stakes are way higher than just some dots on a graph. Well, think about a model trying to predict something as complex as diabetes, but it's only using a few basic data points. It's pretty much destined to be wrong, and here's why.
It's completely ignoring all this critical information. Things like genetics, lifestyle choices, blood pressure, you name it. And by being so simplistic, it's going to make consistently wrong predictions for a huge number of people. That, right there, is the danger of high bias.
So, how do you fix a model that's too simple? Well, pretty logically, you give it more to learn from. You can add more features, more types of relevant data, or you can just switch to a more powerful, more complex kind of model. One that's actually capable of understanding those subtle relationships.
All right, so let's flip the coin and look at the other extreme. What happens when a model doesn't just learn, but it tries way too hard?
Now, instead of that rigid, straight ruler, imagine you're drawing a frantic, zigzagging line that perfectly, and I mean perfectly, hits every single one of those practice dots. It might look like a masterpiece, like it's 100% correct, but it's actually a trap. And this trap has a name too. It's called overfitting. The model has essentially just memorized the training data. It's learned all the random noise, all the little quirks that aren't actually part of the real pattern. It becomes so specific to its training that it's completely useless when you show it anything new. For instance, think about a loan prediction model that just goes totally off the rails. Instead of learning the fundamental signs of financial risk, it starts getting obsessed with completely unimportant details from past loan applications it was trained on.
It might learn some bizarre, totally false pattern, like, maybe that people who buy coffee on a Tuesday are a bad credit risk, just because of some random coincidence in the training data. See, it's learning noise, not the signal. So of course it fails miserably when it sees a real new loan application.
To fix this, you can actually simplify the model by telling it to focus on fewer, more important features. Or, and this might sound a little weird at first, you can give it even more data. By showing the model a much wider variety of examples, you can help it learn the real underlying patterns instead of getting distracted by all that noise.
So we've got these two extremes, right? We have underfitting, which is too simple and just misses the point entirely. And we have overfitting, which is way too complex and gets lost in all the tiny details. And guess what? Both of them lead to bad results.
So the huge question, the one that every data scientist has to answer, is how do we find the perfect balance? How do we navigate between these two problems to build a model that actually works?
Well, the goal is a balanced model, and you can see what that looks like right here. It's not a rigid straight line that misses the trend, and it's not some chaotic squiggle that's memorized every single dot. It's this beautiful, smooth curve that gracefully captures the important signal from the data without getting distracted by all the random noise. That's the sweet spot.
Now, this table just sums up the whole push and pull perfectly. Look at that top row. When a model is underfitting, you've got high bias and low variance. Result, poor performance. Now, the second row, overfitting, is the opposite. Low bias, high variance. Result, still poor performance. And here's the key thing to get. As you try to fix one of these problems, you can easily make the other one worse. It's this fundamental law of machine learning. Finding that low sweet spot in the bottom row, that's the real art and science of it all.
So, and this is so important, this whole thing isn't just some technical exercise for data scientists to worry about. This balancing act has serious, real-world consequences for all of us.
And that's because getting this balance wrong can lead to outcomes that are profoundly unfair, outcomes that really affect people's lives. Denying someone a loan, a job, or even a correct medical diagnosis, all because the model just wasn't built the right way. To fight against this, experts use a really powerful technique called subgroup analysis. This is so critical because it means they don't just look at a model's overall accuracy. Nope, they dig way deeper, and they check to see if it works fairly and equally for everyone across all different kinds of communities.
And this brings us right to our final and maybe the most important takeaway from today's explainer. As we rely more and more on AI to make these huge decisions that affect our lives, we have to keep asking this fundamental question. When an algorithm makes a choice, who is ultimately accountable for making sure these powerful systems are fair, are just, and are balanced for all of us?